welcome to another CHEM271 tutorial. This tutorial is a very quick one on enzyme energetics. So we will be going over two practice problems here. This is the first practice problem where the reaction glucose plus ATP turns into glucose 6-phosphate and ADP. We want to find delta G. Delta G gives us the Gibbs free energy for the reaction and tells us if the reaction is spontaneous or not. And we are given that the delta G with the dot, so this is delta G at standard conditions, so standard temperature, pressure, all reactants, products are at 1 molar. So at these standard conditions, we have a delta G of -4 kcal per mole. We know it's at 25 degrees Celsius, and we're given R, so this is our constant in the equation. The units of R in this case are in calories divided by mole times Kelvin. We are also given the concentrations of everything. So this is fairly straightforward. What we do is we substitute all of these into the equation. The equation that you need to memorize is delta G equals delta G dot, so this is at standard conditions, plus RT ln K. So R is the constant, T is temperature, K is the equilibrium constant, right? And in this case, for this reaction, remember the equilibrium constants are the concentrations of the product multiplied together divided by the concentrations of the reactants multiplied together. So in this case, it's the two products, glucose 6P times ADP divided by glucose glucose times ATP. All right? So that's how I got this expression. So I just took the K, the equilibrium constant, and turned it into this, which is the two products multiplied together divided by the two reactants multiplied together. So now we can just sort of substitute into this equation, but we do need to make sure all the units are correct. So the units of R in this case are calories divided by mole times Kelvin. So we need delta G at standard to be in calories per mole. So right now it's in kcal. So as you get there, we just multiply by 1,000, and we get that this is equal to -4,000 cal per mole. All right, next thing to do is to convert the 25 degrees Celsius into Kelvin. So when we do this, what we have to do is Kelvin is equal to 273 plus the Celsius. So Kelvin, in this case, is equal to 273 plus 25, which is equal to 298 Kelvin. Okay, and then that should be everything. We can keep all of the reactant concentrations the same because they all have the same unit of millimolar. So what we can do now is fairly straightforward. Delta G is equal to delta G standard, so minus 4,000 calories per mole. Remember to keep all your units, plus 1.98 cal per mole Kelvin. So this is our G, right? Or sorry, our R, and then we multiply this for our temperature, 298 Kelvin. I'm going to run out of room, times the ln of this expression, okay? So the expression is glucose 6P, so 0.1 millimolar times the ADP, 1 millimolar, all divided by glucose, so 55 millimolar, and ATP 5 millimolar. So when you put this entire expression into your calculator, you get that delta G is equal to -8,700 cal per mole, which is equal to -8.7 kcal per mole. So this is negative, so what does the negative delta G represent? This means the reaction is spontaneous, so it does not require an input of free energy in order to occur. This says nothing about the rate of reaction, just about how likely is the reaction to occur, okay? And this makes sense given that we have a lot of glucose present, we have a lot of these reactants present, and we don't have a lot of products. So therefore, the reactants are going to react and form products in order to reach equilibrium, all right? And that's it for this problem. So this is the second question of the enzyme energetics problem set. This is the last question. So for the reaction glucose 6-phosphate converting into fructose 6-phosphate at pH equals 7 and 25 degrees Celsius, 1 molar of glucose 6-phosphate and 1 molar of fructose 6-phosphate will equilibrate to this ratio of 2.43. So what we can see is that this is products divided by reactants, so this is actually K, our equilibrium constant here. So we want to know what is the standard free energy of the reaction at pH equals 7 and 25 degrees Celsius. Remember, 25 degrees Celsius is 298 Kelvin, right? Same as the last problem. So in this case, what we're trying to calculate here is the delta G at standard conditions, okay? And we can do this because we know this is at equilibrium. So it's important to note that at equilibrium, delta G is equal to 0, and this is because the reaction essentially stops. So the rate of the forward reaction is equal to the rate of the reverse reaction, so there's no net gain or loss of free energy. So this is because the reaction stops. So because of this, we can actually rearrange this equation. We can subtract the delta G standard from both sides and get delta G standard negative is equal to RT ln K. So now what we can do is substitute in all of these variables. So we notice that we forgot to write it. So in this case, R is going to be equal to 8.3145 joules per mole Kelvin. So this is different than the R last time. It's just different units. So in this case, we're using joules. Okay? So joules are just another unit of energy like calories. So in this case, we can say our delta G is going to be equal to negative, so I'm just going to move the negative over to this side, RT ln K, so R is equal to 8.3145 joules per mole Kelvin, and temperature 298 Kelvin, and we know our K, so ln 2.43, and here we get that delta G at standard conditions is equal to negative 2,200 joules per mole, which is equal to negative 2.20 kilojoules per mole. Okay? So essentially, this is our delta G at standard conditions, 1 molar of each reactant, and we know that delta G is negative, so this is spontaneous. So at standard conditions, this is going, the delta G will favor formation of the product, fructose 6-phosphate, okay? So there will be a net release of free energy from this reaction proceeding in the forward direction, meaning it is energetically favorable, all right? So the next question, in the cell overall, delta G is equal to negative 1,400 joules per mole. So we want to calculate this ratio again, which this ratio is equal to K. So we are using the equation again. Delta G is equal to delta G standard plus RT ln K. All right, but this time what we're doing is we're solving for K. So we need to do a little algebra here. So I'm going to subtract the standard delta G from both sides again. So delta G, this time it's not equal to 0 because we're not at equilibrium. All right. So this time K is going to differ from equilibrium, okay? So delta G minus delta G standard is equal to RT ln K. We can divide both sides by RT. Delta G minus delta G standard divided by RT is equal to ln K. And we know how to get rid of ln. We do e to the power of both sides, so we get e to the power of delta G minus delta G standard all over RT is equal to K. So now what we can do is we can substitute in these variables. So we have delta G standard from the last one. So essentially what we get is K is equal to delta G, so that's given in this problem, minus 1,400 joules per mole. And then we subtract negative 2,200 joules per mole. And this is e to the power of this whole expression. Forgot to put that. And then we do R, so same R as last time, 8.3145 joules per mole Kelvin, and temperature 298 Kelvin. So this whole expression here is e to the power of this whole thing. All right, so if you're doing this in your calculator, calculate this expression first and then do e to the power of that. And what we get is k is equal to 1.38, which is greater than 1. So in this case, the products are still favored, so the reaction will still proceed in the forward direction as stated, but less so than at standard conditions. The rate of reaction will be a bit less. However, energetically, the formation of the products will still be favored. So that is it for this video. Thank you for watching.